Okay, the quiz problem was multiply x to the fifth minus 3x cubed plus x by 2x to the fourth plus x squared plus 7. Now, what people are doing, typically you do the x to the fifth, you multiply it by each of these, then you do the negative x to the third, multiplied by each of these, and then the x, and you multiply by each of these, okay? And that's perfectly all right, but I'm going to do it completely using the distributive law, okay? So this would be, you could write it as x to the fifth times 2x to the fourth plus x squared plus 7. Minus 3x squared times 2x to the fourth plus x squared plus 7 plus x times 2x to the fourth plus x squared plus 7. Okay, now this step is more or less optional, but you should at least think it. But this is actually what you're doing when you multiply this by all these and then this by all these and so forth, because that's exactly what it says. Now, the step that I do really recommend to avoid possible errors is write out the two things that are being multiplied each time. Okay, because if you do it in your head, you're 10 times more likely to make a mistake. Okay, takes a little longer, but doesn't take that long. And then plus, well, minus, and this is strictly not really according to the rules, but it's close enough that it's okay. It really should be plus a negative 3x squared times that, plus a negative 3x squared times that, and so forth. I want to get two people. Okay. Now that's the step that I think is important to write out. If you want to be accurate, if you're in a hurry and you want to take a chance of messing it up, you can kind of skip this step, but I don't recommend you do that right now. You want to reinforce it and you want to have everything right at every step. Then, of course, x to the fifth times x to the fourth is x to the ninth, and you got the 2, so you get 2x to the ninth. X to the fifth times x to the seventh is x to the second is x to the seventh, and x to the fifth times 7, we're going to write it 7x to the fifth. Okay. And then we do this. X squared times x to the fourth is x to the sixth. 3 times 2 is 6. We have negative 6. X to, let's say fifth, x to the sixth. X squared times x to the fourth is x to the sixth. Okay. And then everything else is going to follow. I'm going to say everything because I keep talking, I'll make a mistake. Okay, now you got a 2x to the fifth here. One mistake I saw was what's x times x squared? It's x cubed. I haven't written a 2 in front of this. It's easy to just slip up and write a 2 in front of this. But if you're looking at this, you're going to see there's no 2 there. Okay. That's kind of mistake that people will typically make. Anyhow, there it is. Now we've got to collect our terms. In other words, how many x to the sevenths do we have? Well, I don't see any other x to the sevenths. How many x to the fifths do we have? Well, got 1 here and 1 here. Okay. X to the sixth, and actually I should have done x to the sixth before I did x to the fifth. So just put this in better form so I don't have to rearrange the order of these terms. Now there's only one x to the sixth term, it's minus 6x to the sixth, but then it's plus 9x to the fifth. Okay. And then x to the fourth, we only got one x to the fourth term, so it's minus 3x to the fourth. We got an x cubed. We'll take the x cubed out of there. And we have the minus 21x squared. Then our 7x on the end. And I think that's everything. But we can kind of go through and check. Do we have this? Yeah, we got this. So that's good. Do we have x to the seventh? Yeah, that's the x to the seventh. Put a check mark there. Some people want to cross these out. Well, they're not canceling. And if you're going to use cancellation, you probably want to say crossing it out for cancellation. Okay. But it's okay. I wouldn't penalize it. Then we have our minus 6x to the sixth, it's right here. The x to the fifth terms are here and here, and they combine to give you this. And the x to the fourth term, there's only one, it's right here. Here it is. Then we have an x cubed term, right there it is. We have an x squared term, right there it is. And we have our 7x. So I've just gone through and done some careful bookkeeping to make sure that I haven't forgotten anything or left anything out. Okay? Whatever way you want to do that, it's a good idea to do it. But I think everybody understands that completely. Because I only saw one small mistake in all the work that I looked at. Okay? Now, I didn't look at all the work as carefully as I might have. So if you got something different than this, one of us is wrong. Okay. And you can check and see which one it is. But the process is pretty straightforward and everybody followed it. Okay, now I just asserted the 2 to the 30th power is about equal to this number here. Then I realized, wait a minute, no. If I do 1.05 to the third power, it's probably more like a 1.6 or 1.7 here. And you don't have to understand what I just said. It's binomial expansion. We probably get to that. Kind of an important thing, but right now you wouldn't know. Just an extension of distributive law. Okay. So that's not exact. If you put it in your calculator, it might be a 1.6 something. I think it'll be at least a 1.6 there. I don't think it'll be a 1.8. Now my point is, how big is that number? Well, it's bigger than anything you can imagine. Probably. Okay. Let's say BBs are small, right? Let's say I put a string of 1,000 BBs. How long would a string of 1,000 BBs be? Is it more than your distance between your outstretched arms? Or less than the distance across your hand? What do you think? How far do you think it is? Think it's more than this? Okay, well, we could put a meter stick down. I think a BB is about 3 millimeters. It's going to turn out it's going to be a little further than my outstretched arms. Okay, it's going to be about half again that much. It's like the floor to the ceiling in a somewhat taller room. Okay, that would be a string of 1,000 BBs, roughly. Okay, now let's say we did 1,000 rows of 1,000 BBs. So we could lay them out on the floor. It'd be roughly ballpark 10 feet by 10 feet. How many BBs would you have then? There are 1,000 BBs in each row in 1,000 rows. Well, yeah, let's see if anybody wants to tell me. Yeah, I've got a good answer since a million. Yeah, yep. It's a million. 1,000 times 1,000 is a million. Yeah, that should be common knowledge. And if it isn't, you know, really kind of think it through and see if you can't understand that. So if you want to go to a billion, well, a billion is 1,000 billions. So that means we're going to have to stack 1,000 layers, each with a million. And it's going to be a little higher than the ceiling. It's about 10 feet tall. Okay. So that'd be 1 billion. How long would it take you to count those out? We only live for around 3 to 4 billion seconds if you live a full life. Okay. I think I'm up to 6 billion now, but that's kind of unusual. Okay, seriously. You've got 86,000 seconds in a day, 365 days in a year. Okay, round that off to approximately 100,000 for approximately 300 days. Okay, gives you 30 million in a year. Then in 30 years, you get 1 billion. So if you're putting those down one at a time to make that stack, take a big chunk of your lifetime. It's a lot of babies. Okay, well, that's a little over 1 billion. Okay, that's about it. If these were zeros, that would be 1 billion. Okay, so you can visualize a 10 by 10 by 10 stack of babies. Now, if you use optimal stacking procedures, you can probably get it 10 by 10 by, well, probably 8 by 8 by 8 maybe. But it's a bunch of babies. Okay, so well, enough about babies. Well, we want to write that as 1.17 times 10 to the 9th, because even looking at this, you kind of go blind with all the zeros. This tells you how many zeros there are. It's what's 10 to the 9th. It's 1 followed by 9 zeros. Okay. So actually, I could write this in 2 steps. I could say this is 1 times 1.17 multiplied by 1. That's 1,000. 3 more zeros is 1,000,000. 3 more zeros is 1 billion. Okay, does that halfway make sense? How many molecules do you think there are on the tip of my thumb? Good heavens, my fingers don't go that far. That much of my thumb. That's the trigger finger. Okay. How many molecules in there? Well, between 10 to the 23rd and 10 to the 24th. Okay. Is that bigger than this? Yeah. Yeah, molecules are really tiny. Okay, you can't see them. There's nothing that visible light can do to help you see a molecule. Okay, you can use shorter wavelength light, higher energy, but you tend to blow the molecules apart if you do that. So you do tricky stuff with electron microscopes and stuff like that, scanning electron microscopes. So you can actually image these things, even though you're not imaging them with visible light or even higher frequency electromagnetic radiation. So that's about 10 to the 24th. What's the, and let's just say I've got a better measurement than somebody's thumb. There's probably somebody out there whose thumb has 8 times 10 to the 24th molecules in it. I just want to put a number on that, okay? Okay. How many thumb tips do you think it would take to have the same weight as a liter of water? Let's not get into a test about it. Let's say you got little plaster models of thumb tips. Okay, not real people's thumbs, right? How many of those do you think would weigh the same as a liter of water? Okay, well, half the class thinks it's more than 100, and the other half thinks it's less. So I'm going to compromise, and I'm going to say it's about 50. Okay, I think it's about 100, isn't it? I mean, right ballpark. Okay. Each of these has a mass of about 150, 100 kilograms. Okay. How many kilograms in typical human body? What do you think, metric? Or you want pounds? Okay. Let's say fairly typical human body, 180 pounds. Okay. That includes men and women. And there are a lot of big men around. Okay. A lot of 400 pounders. Okay. And there are a lot of small men, you know, in between. Let's say 180 pounds is average. So, okay. 180 pounds is about ballpark 90 kilograms. There's enough information there to determine how many molecules there are in an average human body, or to estimate. It should be a rough estimate. We can be off by a factor of 2 or 3 when you do this. But so how would you determine, write it out. How would you determine how many molecules in an average human body? If you assume that number of molecules per unit of volume in a thumb is about the same as the average number of molecules per unit volume in a human body. So you use these 3 numbers, figure it out. So write it out for me. Okay, number of molecules in a kilogram would be what? Number of molecules in a thumb tip times the number molecules in the thumb tip times the number of thumb tips would have a mass of 1 kilogram, right? Now there's an easier way to write that. Well, I'm going to write it twice. Okay. Yeah, there's something that needs to be explained here. We're engaging a little bit. We know what tip means. molecules per tip times tips per kilogram. Okay? Does that make sense? This is number of molecules for one tip, which is the number of molecules per tip. This is the number of tips that would have a mass of 1 kilogram, so that'd be the number of tips per kilogram. Well, per means division, basically. Molecules per tip could be written as molecules over tip. And tips per kilogram could be written as tips over kilograms. Now, if you multiply that out, tip in the denominator divides a tip in the numerator. See twice. And we can write this as 8 times 10 to the 24th molecules per tip times 50 tips per kilogram. And that would be 400. Well, better than 50 times 8 times 10 to the 24th molecules per kilogram. Let me write that up here again so you can read it. That incomprehensible word there is molecules. And that's 50 times 8 times 10 to the 21st fourth molecules per kilogram, which is 400 times 10 to the 24th. I'm having trouble writing CU. I keep wanting to go into cursive and my hand is just being uncooperative. So I'm not doing a very good job of writing molecules. That one isn't bad. Those are terrible. Okay, so anyhow, that's the way the numbers work out. If we multiply 50 by 8 times 10 to the 24th, we get 50 times 8 times 10 to the 24th, because we're multiplying three numbers here, 50, 8, and 10 to the 24th. We can group them any way we want to. So we group the 50 with the 8, and we get 400. And we still got the 10 to the 24th. Okay? Now, 400 times 10 to the 24th, well, $400 is 4 times 10 to the second power. 10 to the second power is 100. 10 squared is 100. Multiply that by 4, you get 400. So we can write it this way. And that's the same as three numbers that we're multiplying. Okay. So we group the last two, the 10 to the second and 10 to the 24th. That's 4 times 10 to what power? So if you're listening, this is a distant student, or have to step out for a minute. You can watch this and try to digest it. Again, the point here now is not so much the molecules per tip times tips per kilogram, but that's important. We want to try to understand that, okay? But what we want to do here is just deal now with this number, 400 times 10 to the 24th. Because of course, if you do 550 multiplied by 8 times 10 to the 24th, you get 50 times 8 times 10 to the 24th. The 50, you multiply three numbers here. So you can multiply any two that you want. So we multiply the 50 by the 8, leaving the 10 to the 24th out here. And 50 times 8 is 400. So we have 400 times 10 to the 24th molecules per kilogram. Now, how do we write that? Well, 400 times 10 to the 24th. Don't forget about the molecules per kilogram. It's kind of important to write that because that tells us what the number means. Okay, but right now, let's just deal with the number now. This is a scientific notation part. Okay, we've got 400 times 10 to the 24th. Now we could write that as 400 and then write 24 more zeros on it. It's much more compact to just use 10 to the 24th. You understand, you don't want to write out all those zeros. Okay, so what's 400? 400 is the same as 4 times 10 to the second. 10 to the second is 10 squared, which is 100, and 4 times 100 is 400. Well, now again, we've got three numbers multiplied together here. We can pick whichever two that we want to multiply first. So we're going to group the 10 to the second and 10 to the 24th. And then the question is, what's 10 to the second times 10 to the 24th? So write that down. It's 10 to the second times 10 to the 24th. Okay, that's not uncommon for somebody to stumble over this because it doesn't look like anything we've done with exponents. All right, but let me just write out here. Okay, let's see. We're trying to figure out well, of course, we could write 1 followed by 2 zeros. That'd be 10 squared. That'd be 100, right? And then 1 followed by 24 zeros. Okay? And then we multiply them together and figure out how many zeros we've got. That would work. But probably easier if you just think of this. What's x squared times x to the 24th? Well, everybody immediately sees that that's x to the 26. Everybody would immediately see this if everybody's done the homework and done pretty well on it, okay? Which is the case for this assignment. Everybody here and everybody in the distance class did well to perfect on the assignment, okay? There are a couple little glitches, but we think we straightened those out. Okay, so we got x squared times x to the 24th. That's x to the 26th, right? So if you take the second power of some number times the 24th power of some number, you get the 26th power. And if x had to happen to be 10, as it is here, you would get 10 to the 26, just using the rules of exponents. A number to the second times the same number to the 24th is that number to the 26th. Okay, so we want to be really clear on that. And the open math assignment will help reinforce this. Okay, so now we have then, this is 4 times 10 to the 26. Okay. Now this is scientific notation. This is the number If the number is greater than 1 and less than 10. Okay, has to be greater than 1, has to be less than 10. 400 doesn't fit this, so this isn't scientific notation. But I can write 400 as 4 times 10 to the second and multiply it out and get scientific notation, right? If I write this as 4 times 10 to the second, then this is in scientific notation, and so is this, okay? And when I multiply them, I still get the 4. It's still in scientific notation. Now, sometimes if you have 4 times 3 times 10 to the 22nd, you get 12 times 10 to the 26th, and you'd have to write that as 1.2 times 10 to the 27th. We'll talk about that. And here's the power of 10. Okay. Now, this example shows us why we want to use scientific notation. Now, tell me, if the average human body is 90 kilograms, how many molecules would that be? We've figured out the number of molecules per kilogram, right? And now you've got a number of kilograms. So how do you get total number of molecules? Okay, so how many molecules in a typical human body? Well, we were given information about the approximate number of molecules in a typical thumb. And if we assume typical thumb is typical of the, well, let's say a typical thumb just has a typical mass, okay, of human tissue. Okay, so I didn't say that very well, but okay, we've got this many molecules per thumb tip, and 50 thumb tips would make up a kilogram. Okay, and we multiply this by this because it's pretty obvious. If you got this many in each one, then you got 50 times that in 50 of them. Okay, and that's in a kilogram. So that's what we got. That's our 4 times 10 to the 26, meaning 4 times 10 to the 26 molecules per kilogram. Now, what other information do we have? We've used this information and this information. Average human body, 90 kilograms. Okay. How many molecules would that be? Assuming that you have as many molecules per kilogram. Well, I'm going to say just to keep track of the meanings because it's easier to think it through if you remind yourself every time what this means. Okay, 90 kilograms per body. Okay, you multiply that by 4 times 10 to the 26. Molecules for every kilogram. Every kilogram has this many molecules. You got 90 kilograms in a body. So you're going to multiply those. You get the number of molecules per body. So let's just do the numbers. We do 90 multiplied by 4 times 10 to the 26. So remember how I did this calculation. We got 3 numbers multiplied together. We can pick which 2 we want to start with. So what 2 numbers would you multiply, and then where would you go with that? Okay, so what do we have here? We have this. 90 times 4 is 360. Okay. And 360, if you think about what we did over here, we have to have a number out in front that's between 1 and 10. This is not scientific notation yet, just as this wasn't scientific notation. $360 is 3.6 times 10 squared multiplied by 10 to the 26. And we probably don't need this anymore. Good thing, because we need the space. There we have 3.6 times 10 to the 28th. Oh. Okay, now off the top of my head, I remember most of these numbers, but I think one of them, particularly the number of galaxies in the universe, is a little more than the previous estimates that I've used, okay? I just looked out and I saw more than that. So it must be bigger. Seriously. With a Webb telescope and everything, this estimate seems to keep going up. Maybe more like 300 billion, maybe more like 1 trillion. Anyhow, Earth's mass, about 6 times 10 to the 24th kilograms. Sun's mass, about 300,000 times the Earth's mass. Galaxy, 100 billion sun masses. Universe, I'm going to say 300 billion galaxies. So if you've already done it for the 100 billion, okay, just multiply your result by 3. 300 billion galaxies. Assuming 8 times 10 to the 25th atoms per kilogram. And most of the atoms in the universe are light atoms, like hydrogen and helium. Then up to carbon. And after that, they get rarer. So that might be a fairly decent estimate, but I did it in my head. Based on Avogadro's number, the mass of carbon atom. Okay. And what a molecules. So what we say here is this means kilograms per Earth mass, but I don't want to write out all the words. Plus 300,000 Earth masses per sun mass multiplied by 100 billion sun masses per galaxy multiplied by 300 billion galaxies per universe multiplied by 8 times 10 to the 25th atoms per kilogram. Okay. So this is 3 times 10 to the 5th, and I'm not writing out the meanings anymore. Because I want to, okay, 100 billion. A billion's 10 to the 9th. 100 billion is 10 to the 11th. Interpreting all these numbers, putting that in scientific notation, this and this. They're the numbers. This equals what? The numbers out in front are 6 times 3 times 8. Okay, since all these are multiplied, we should, oh, there's another 3. So I get the numbers 6, 3, 3, and 8. Times 10 to what power? We multiply 10 to the 24th by 10 to the 5th and so forth. You're going to get 10 to the 24th plus 5th plus 11th plus 11th plus 25. Okay, well, the rest is pretty simple. That's 54 times 8, which is 532, I think. So it's approximately 5.3 times 10 to what power? 24 and 5, 29. Add 11 is 40. Add 11, it's 51. Add 25, it's 86. Now, if we consider that your typical atom has a mass equivalent to about 3 quarks, we could get the number of quarks in the universe and then double that to get, well, we wouldn't double that. Multiply that by the number of electrons and all that stuff, and then take into account all the weird particles. Well, the number goes up a little bit, maybe up to 10 to the 90th or so. Maybe beyond that, if you count photons and everything else. But it's not going to reach anywhere near 10 to the 100. The universe is a big place. But you can express the number of atoms in the universe by numbers that you understand. They can't really comprehend 10 to the 86, and neither can I. But that would be it. So I'm just curious. I'm going to look at out here and see if Google will tell me something about this. Okay, well, Google or something, some search engine, I don't know which one we defaulted to, probably Google, tells me 10 to the 80th approximately. Obviously, Google doesn't know as much as I do. So I think these numbers are relatively correct. Then I ask how many subatomic particles. Well, there are a whole lot of subatomic particles associated with an atom, okay? And other particles that are parts of atoms. And they say, oh, about 10 to the 80th. Okay, I think they're wrong about that, but then they revised that and they said, well, we think it's somewhere between 10 to the 80th and 10 to the 97th. And this is kind of right in the middle, okay? So I'm going to stick with my estimate. Then maybe I'll ask them to detail how they got their estimate that's low by a factor of about 1 million, okay? Mine might be high. And the other thing is, most of the particles in the universe aren't in atoms because they're in stars. And they're just all broken apart into a bunch of subatomic particles. Okay, mainly I'm trying to give you an idea of how scientific notation can be useful for writing really big numbers. And that's one of your assignments. Now, another one is negative exponents. So let me give you a quick synopsis of negative exponents. What's 2 to the first power? Show me your fingers, it's 2. What's 2 to the second power? 4. What's 2 to the third power? 8. You don't multiply 2 by 3, you multiply 2 squared by 2. That's 8. 2 to the fourth power is 16. Each of these numbers is 2 times the one before it. Okay? So if we go from here, how does this number compare to this? Half as big, right? This is half of this, this is half of this, this is half of this. Okay? So what should 2 to the 0 be? Show me with your fingers. It's not 0. Half of 2 is not 0. 1. Keeps going by half. So what's 2 to the negative 1? What's half of 1, which is 1/2? 2 to the negative 2 is half of a half, which is 1/4. And so forth. Okay? That makes sense? Well, so we say two to the negative 1 is then 1 divided by 2 to the 1, right? Makes sense? Well, it's 1/2, and what's 1 over 2 to the 1? It's 1 over 2, which is 1/2, right? So what's 2 to the negative 2? I'd ask you to write it out real short on time. Okay, 2 to the negative 2 equals, well, it's 1/4, but how do you write 4? It's 2 to the second. Right? So write 1/4, I can write 1 over 2 to the second. So what do you think 2 to the negative 7 would be? Well, there's a pattern here. 2 to the negative 2 is 1 over 2 to the 2. 2 to the negative 7 would be 1 over 2 to the 7. And if we kept going with this table, we'd get to 2 to the negative 7 pretty soon. Be 1 over 128. Okay? And 128 is 2 to the 7. If we went up here, we'd find that. So we have a definition. X to the negative p is 1 over x to the p. Also, x to the 0 has to be 1. If 2 to the 0 is 1, well, you could do the same thing with any base. Doing something similar to what we've done, you would have to conclude that if we're going to be consistent in the pattern, that x to the 0 has to be 1. Okay? Now, your homework is on negative exponents and scientific notation. Okay? And you do have some negative exponents in scientific notation. You might even want to do the negative exponents assignment before you do scientific notation. Okay? And we've got a question, so we'll just wrap up. And if question something everybody needs to hear the answer to, I'll add it in a minute.